So today we have the pleasure of having the Orlagh Creevey to give a talk, a seminar. So let me introduce her a little bit. But I have many things to say actually. So Orlagh actually started, came here to the IC like 20 years ago for doing her master. She was doing a becaria in the pyramid. And then she did her what we call the DA, and then like the master at the University de la Laguna. Then she got her PhD in 2008 in collaboration, so at the ULL and the High Altitude Observatory in Boulder, where she had many supervisors between Juan Antonio Belmonte, Sebastian Jimenez Reyes, and at HU, Tim Brown and Travis Metcalf, where she was working on astroseismology and binary systems. Then she did a first postdoc at the IC from 2008 and 2010, working as well with Pere and the some observations, doing the astroseismology, preparing Kepler data analysis. And then in 2011, she did a postdoc at the Observatoire de Nice in France, working on astroseismology again and more with interferometry. And she became in 2013 part of the Gaia project. Then she did another postdoc at the IS in Orsay, working on brain activity of stars with Frédéric Baudin. And in 2014, that's when she got her permanent position at the Observatoire de Nice as an astronomer. And so she's working mostly, as you can see, on Gaia now, and preparing also Plato benchmark stars for the future. So I think that's all I can say about Orlagh, and we're very excited to hear about your talk. So please go ahead.
Okay, thanks very much, Savita. Yeah, I'm very happy to be able to talk to some of the old colleagues at the IAC. So today I'm going to talk about something I didn't talk about when I was physically at the IAC. So I'm going to talk a little bit about Gaia DR3, but more in particular, the astrophysical parameters in Gaia DR3. Okay, so this is a talk that, it's more of an informative talk rather than showing you nice results, because as you know, the release is not for another 2 weeks, and there's limited material that I can show you. So this was prepared with many of my colleagues. I've just listed 3 of the more active ones for the preparation of the talks. But this talk is given on the behalf of the full Gaia DPAC, and this is the CU8 team. So we're over 70 members, and I'm presenting basically results that are coming out from this big team. Okay. So let me just give you a brief overview of what I will talk about today. So let me remind you first that Gaia DR3 is on June 13th in 2022. And there's a link here if you want to go directly to have information about what's going to be there. Then these next 3 will be quite quick. I'll go through these. So I give you an overview of Gaia and its observations, because I'm aware that there are students and young postdocs who may not be very aware, or even more advanced people who may not be interested in Gaia. So I'll give you a very brief overview of what is Gaia, what it does. And then I will talk a little bit about the Data Processing Analysis Consortium, which is DPAC, and in particular the Coordination Unit 8, that's the CU8. So this is the unit that deals with astrophysical parameters. I'll also give you 2 brief slides on what's the difference between Gaia DR2 and Gaia DR3. So what is it that you should be looking forward to? So, and then for most of my talk, I will concentrate on astrophysical parameters in Gaia DR3, okay? So maybe 10-15 minutes here, and then the rest of the time on this, along with a very brief summary. Okay, so as I will be talking about astrophysical parameters, let me directly give you the main papers with all of the information if you want to know what's in there in more detail, because I cannot tell you everything, of course. So the main paper will be Creevey et al., which will give the general content of the astrophysical parameters, including methods and models that are used. Then there are two accompanying papers. So the first one is Fueno et al., and this paper focuses on the results for stellar parameters. But of course, astrophysical parameters is not just for stars, it's also for anything that Gaia sees, like quasars and galaxies, etc. And so this second paper, this third paper, Del Chambre et al., focuses on more detail on the non-stellar content. So I will give you an overview of what these products are later. Okay. So let me begin with an overview of Gaia and its observations. Okay, so here I'm just showing where Gaia is. This is the sun, this is the Earth, and Gaia is here behind the Earth, pointing away from the sun, of course. And what it does is it rotates like this, okay? And basically it observes all parts of the sky. So this is a picture of the satellite. Can you see my mouse? Yeah, okay. This is a picture of the satellite, and it was actually launched in 2013 for a nominal 5-year mission. So the nominal mission finished in 2019. Okay. Oh, sorry. I'll tell you 2019 because, in fact, we added a few months to the nominal mission. Okay. There are about 450 scientists and engineers. Currently, there's enough gas to continue observing until the end of 2024. And the final mission extension will be approved next year. So we will know if we will continue till 2025 or if we stop at the end of this year or a few months into the next year. So as you can see, if we go to the end of the mission, we're basically going from a 5-year mission to a 10 to 11-year mission. Okay, and this is extremely important for getting very high precision and reducing systematic errors on the products. Okay, so the goal of Gaia is to measure the positions and the motions of 2 billion stars. And this is 1%, approximately 1% of the Milky Way. And using this information, we want to then understand the formation and evolution of our galaxy and everything that's inside it, and also outside. The Gaia itself is actually inclined with respect to with respect to the sun. So this means it actually precesses, okay? So it actually makes a small wobble, and it continues this wobble as it's also rotating, okay? So here what I'm showing is basically the sky, the part of the sky that it covers every time it rotates. So as you can see, it will cover this part of the sky in 6 hours, then it will do another like this, then another like this, and it will continue like this. This is an example of a 12-hour coverage. And you can see that there are certain places where Gaia observes a lot more, like here, and then there's other parts where it observes a little bit less. And this information you will find in Gaia DR3, which will tell you the number of observations. Okay, so obviously with higher observations, we have higher precision. Okay, so what exactly does Gaia observe? So here I'm showing the focal plane of Gaia, and basically a star will come along from here, okay, and then it will move across the different parts of the focal plane, and there are several different parts to this, okay. So the first part here is the astrometric field. Well, the first part is Sky Mapper, but I'm not going to talk about that. Is this astrometric field, and this is where they get what is called the G magnitude photometry. So they use this basically to get the astrometry, but along with the astrometry to get the precise positions of the stars, then they use this to reconstruct the photometry. Of course, the astrometry then means that we measure the position of the star very accurately over a long period of time. And basically every time that the source is observed, it has one of these points on it, okay? So these small circles here is an indication of how far or how close the star is to us. So if this star is much closer, this will do a much larger circle. This is the parallax effect. And this movement in this direction here is the proper motion of the star. So as you can see, if we only have 1 year, we can get some confusion between the parallaxes and the proper motions, whereas as we get more and more data, so over 5 years, we can resolve the astrometric solution. Now, of course, if there's a binary system in here, it'll have other wobbles on it, okay? So the longer data we have, the more accurately we can solve the astrometric solution. And this is how we get the very precise positions and movements of each of the sources. Then moving along here, there are the blue and the red prisms. And basically this gives spectrophotometry. And they are in fact prisms, more specialized prisms, and it disperses the light. Okay, so it's not a spectroscope, but it disperses the light. And then finally, the star will move along this part. And this is the Rvs Spectra, so the radial velocity spectrograph. And it produces what's called high resolution. Okay, this is up to you if you want to think of this as high resolution. It's about 11,000 resolution. And you can see very clearly there are some lines that we can very clearly identify. And this is just one example of the Rvs spectra. Okay, so there are the different observations from Gaia. So now what I want to do is present briefly the DPAC consortium, because it will help you also understand which data are going to be available in DR3. Okay, so here we have just an overview. This is an organigram. Forget about this part. All we're interested in are the people who actually do the work. So, well, we all do the work, but these are the different coordination units, 1, 2, 3, all the way up to 9. Okay. Okay, so let me begin with just this one. So the CU3, these are the people who do the astrometric solutions. So they measure the positions, the proper motions, and the parallaxes of all of the sources. Then we have another here, another 2 units that focus on the spectra. So this CU5, you don't have to remember the number, focuses on the photometric processing, but this is the prism spectra. So they produce these BP and ORP spectra. I will show you some more I'll show you examples of these later. Then this CU6, they produce the Rvs spectra, and they also produce other things like the radial velocities. And the idea of doing these spectra is, of course, to do the radial velocities. Being able to exploit the spectra for to get stellar parameters is kind of an addition to this, right? But the main objective is to do radial velocities, because this will give, along with having the astrometry, you will have the movement, but you'll have the actual the last dimension of the movement. So you have the full astrometric solution and movement of all of the sources. The Rvs spectra, of course, can only observe to brighter targets, so roughly around 16th magnitude, whereas for the BP and the ORP and the astrometry, it goes down to magnitude of 21. Okay, so what I've just presented to you are, let's say, the main raw data products that have been produced, and you have seen most of a lot of their results in Gaia DR2, Gaia DR1, Gaia DR2, and early data release 3. Okay. Then there are all of these other coordination units. So, and this is what you're going to see in DR3. So this particular one is called non-single stars. So it analyzes anything that's not a single star. So that could be a solar system object. It could be multiple systems like binaries. It could be extragalactic sources along with other products. Okay. Then there's also variability processing. So these analyze the variability from the time series. So they produce frequencies or rotation periods among many, many other products. And then there is the CU8, the astrophysical parameters. And this is what I will be focusing on today. It's what's coming out of this coordination unit, okay? And it's important to understand that we produce astrophysical parameters and classification from mean spectra, okay? So this means we cannot analyze very well highly variable sources. If you want to look at highly variable sources, you go to the results from this other, and you can also do this yourself. But here we analyze mean spectra. Okay. So now that I've presented that, I think this will be easier to understand the difference between DR2 and DR3. Okay, so let's begin with early Gaia Data Release 3 versus Gaia Data Release 2. So I don't know if you can see that. Yeah. Okay, so there's very similar products between what came out in 2020 in December, early Data Release 3, compared to DR2, which was in 2018. The main difference is there's much higher quality, okay? And it's higher quality because the astrometry and the photometry was based on 34 months of mission data instead of 22 months, okay? So it's nearly 3 years, which allows us to resolve much better the astrometry and get higher signal to noise ratio in all of the data products. Concerning the radial velocities, so this is a major product from for Gaia also, and basically what came out in DR2, not 22, I hope it's not going to be 22, was basically copied to DR3, and they corrected some things that were found afterwards. So there's nothing new in the radial velocities. Now in DR2, there were some astrophysical parameters. So I use AP because I use this word a lot. And basically effective temperature, extinction, reddening, radius and luminosity. But this was produced from photometry and parallaxes. And this did not come out in EDR3. Okay, so the only astrophysical parameters that are there are still those ones from DR2. And because they were based on this data, they had many assumptions in the parameters. So basically the data model remains very similar to DR2, which the main table is, most of you are probably familiar with this, is Gaia source. Okay, so this is between DR2 and EDR3. So it's primarily the astrometry and the photometry that has been updated with much higher precision. So now, what's the difference between Gaia Data Release 3 versus Gaia Early Data Release 3? Okay, so Gaia Data Release 3 is actually the full release, and it contains a wealth of many new data products. Okay, so apart from this table Gaia source that I mentioned earlier, there are over 40 new tables in the archive. Additionally, there are 200 million BP and Rvs spectra, and there are about 1 million Rvs spectra that will be available for you to download and work with and produce your results on. Then there are also 30 million radial velocities. This is compared to 7 million in DR2. So this is 30 million in DR3, of course, based on 3 years of data. There are many more new variability data. So there were, I can't remember the number, but there are like basically over 11 million objects now in this from this group. So there's anything that's variable, it's going to be there. So have a dig in and see what's in there. There's also binary star characterization. Then there are extragalactic objects, solar system objects, and astrophysical parameters. Okay, so these are all of the new data products. And what I'm going to talk about is only astrophysical parameters. Okay, so these new data products here. Okay, so here we go. For the main part of the talk. So I always think it's important to show the faces who are behind this, because they spend a lot of time and telecons and stressful COVID periods trying to meet deadlines and fix problems and send documents and communicate in order to make a data release possible so that everybody can exploit it. So here are some of these people. This is probably a photo from maybe 1.5 years ago. We were much happier. If we took this photo right today, we'd be all very stressed at the moment. So anyway, this is just a representation of CU8. This is not all of the team. There are a few outsiders also in here. For example, there's Anthony Brown, who is not part of CU8, but he's the chair of DPAC. Among other people. Another not so nice diagram I'm going to show you is CU8, what we produce and how we produce it. Okay, so in summary, we produce classification and probabilities, extragalactic objects, distances, stellar parameters. We look at different regions of the H-rod diagram, chemical abundances, emission line stars, and many other things that I'll explain in more detail. So this is an overview of the actual data producing modules within CU8. So the processing chain is called APSIS, and this runs at Cannes in France at the Data Processing Center. We take the upstream data from CU3, CU5, CU6, so these are the spectra and the astrometry, and then it goes through all of these modules, and we produce many different results. Now, the reason for going through all of these modules is because they all produce or focus on something very specific. And there are 13 of them, and this is why it's probably going to be a little bit complicated for many people to understand, what is in the archive, because we have over 500 parameters and we have to explain this. So, I'm happy to be able to explain it to you. So these, basically, some of these modules produce extragalactic objects. Some focus on interstellar extinction, and then all of these focus on single stars, and this one looks at binary stars. Okay, I'm not asking you to retain this information. I'll explain it in more detail later. But the reason I want you to see the names here, is because in the archive, when you see something, they're actually going to be encoded with the name of the module, because this will help the user know how the data were derived. It will allow you to go directly to any relevant paper or online documentation just about that module, and then you can get many more details. Okay, so in CU8, what we use are the astrometry, okay, I showed earlier. Then we use the BP and the ORP spectra. Okay, so I'm showing here an example of the BP, which are the blue prism, and the red prism spectra. Okay, so it covers basically just past 300 to around just over 1000 nanometers. And what we're showing here are just how these spectra vary with the effective temperature. Okay, so you can see for redder stars, like down at 2500, there's much more emission here in the red. Then much more light in the red than in the blue, as we would expect. So we use these spectra to try to extract the astrophysical parameters. Then we also use the Rvs Spectra. So there's a lot of detail in this image. So you can find this image on the Gaia web pages. So this is the Rvs Spectra. Here you can see the calcium lines. The calcium lines are used to derive things like activity index. There's also a diffuse interstellar band in here. And so there's information about the DIB that has been extracted. And of course, there's the general stellar parameters that you can extract from the global thinning of the spectra. And there are all these individual elements that you can see. So there are many chemical abundances that are also available. Okay, so this is the input data that we use. Okay, so to remind you, in DR2, we used photometry and parallax, and we produced these 5 parameters. Okay, in DR3, we have over 500 fields for up to 1.6 billion sources. And I represent the categories of what we produce in CU8 as this beautiful pie chart. So where, let's see, all of this part here is non-stellar, and all of this part is stellar. So there is definitely something for almost everybody in astrophysical parameters here. So there's a huge amount of information about interstellar extinction. So either source, like on a source by source, or on a HELPIX map. Then there are also classification and probabilities. There's also an outlier analysis. So this means the 50 million objects that are the worst classified, according to this classification here, they're analyzed by what's called an outlier analysis, and they do an unsupervised classification using self-organizing maps. And actually this is done by the team in La Coruña, led by Minya Manteiga and Carlos da Fonte, so many of you may know them. Then there are astrophysical parameters for galaxies and QSOs, primarily the redshifts. So these are also produced by CU8. And then all this part are the stars. Okay, so the majority are the spectroscopic parameters, so extracting the information from the BP, ORP, and the Rvs spectra. And then there are also evolutionary parameters. So I'm going to try to explain a little bit of each of these. I won't be able to explain everything, but it's really just for you to have a panorama of what you can expect in 2 weeks from now and what might be of interest to you. Okay, so first of all, if you want to, how you're going to find it, okay, if you go to the Gaia archive, which is this link here, you can do a search. Okay, so there's a basic search here you can click on if you just have your favorite object, and you can put in the name of this object and you can get some basic information. But most of you will use the ADQL, and if you haven't done this yet, you will be required to learn it. It's very simple, but it's basically telling you to select, find specific parameters from certain tables for a list of sources. Or so there will be lots of help. There is already lots of help on ADQL queries, and there will be plenty of examples that will be available with DR3 concerning the new data products. And if you've got problems, you don't hesitate to send an email to the help desk. So what will you will see in 2 weeks' time, if you do this, you'll get Gaia Data Release 1, 2, Early Data Release 3, and Data Release 3. Okay, so you won't see this right now. I can see it because I have privileged access, but you won't get to see this yet. Okay, so if we just open up Gaia Data Release 3, you'll get this drop-down menu like this. And because there are so many products, it has been organized by, say, category to help the user navigate to what they're interested in. Okay, so for example, the solar system objects are here, the astrophysical parameters are here, extragalactic are here, the variability analysis are here. Okay, so what I am presenting here are astrophysical parameters, and they are found basically in 2 drop-down menus. The first one is the astrophysical parameters, and the second one is the extragalactic. Okay, because the extragalactic, we decided to put everything from Gaia in extragalactic into one extragalactic table. This would make it much easier for users to extract this information. So you can see there are 6 tables here from CU8, and there are 2 tables here that produce data from CU8. Okay, but additionally, there are another 2 tables containing the MCMC samples from some of the modules. Okay, so if you don't want to get just the value of the parameter and the uncertainties, you can actually extract the MCM sample for that source. So you can basically still have the correlations between the parameters if this is what you need for your science. So there are 10 archive tables where you will find astrophysical parameters. Of course, there are many more archive tables where you find lots of other stuff. Okay, so now what I would like to do is just to go into more detail on some of these different categories. So the extinction, classification, stellar, etc. Okay, so let me start with the class probabilities and classification. So, I'll begin with the non-stellar products first, and then I will focus on the stellar products. Okay, so you'll find this information in the astrophysical parameters table, and actually most of what I will talk about today will be found in the astrophysical parameters table. It's the main first table to go to. There are some results are also copied to QSO and Galaxy candidate tables. The reason that these are called QSO candidates and Galaxy candidates is because when we're doing the processing in the R3, we decided that we would rather be more complete and have more errors rather than be more pure and then have less results. So this is why this is called a QSO candidates table and a Galaxy candidates table, because there will be sources in there that are probably stars. Okay, but they had, for example, some emission that made us think that it was a quasar. Okay, so this is provided by one of the main work packages in the APSIS chain, so the C8 chain called DSC. And it produces basically probabilities, so values between 0 and 1. And you will find a field name like this, class probability, encoded by its work package module, so that you can, again, just go directly to the information on DSC if you want more information. And then you have a variety of methods that are used, okay? And then at the end, you have star, galaxy, quasar, white dwarf, or binary. So basically, for one source, you may have a probability of a star to be 0.9, and then a probability of it being a white dwarf of 0.05, for example. But the full probabilities will add to 1. Okay, so using these probabilities, then you can decide yourself what you think this object is. So you might say, well, I'm going to select everything with a class probability of being a star higher than 0.5. Okay, but this is up to you to do, right? But if we take just the galaxies and the quasars, what I'm showing in the figure here is what these galaxies and quasars look like in a color diagram and a color magnitude diagram. And you can see that, so the galaxies are the orange and the quasars are the blue. And you can see that the classification has done a very good job of separating these objects, right? So the objects, the analysis is not just done on colors, it's also done on the spectra, which is this spec mod. It's done on the astrometric and photometric properties, which is this ALOS mod. And then there's another result that combining the results for both of these. Okay. Now, if we go to the QSO and the galaxy redshifts, so you'll find these and the QSO candidates and galaxy candidates table. So the first module here is the UGC, which is who looks at unresolved galaxies for redshifts between 0 and 0.6. And you'll find results for about 1.4 million sources. And here I'm showing a comparison of the redshift from UGC with what is known in the literature from the SDSS survey. And you can see that there's very good agreement. Of course, there's some dispersion, basically indicating the reliability of the results. From QSOC, so QSOC is the QSO classifier, and it extracts the redshifts for QSOs with values between 0 and 6. So here there are over 6 million candidates. So this particular table is much more complete rather than pure, because we don't believe there are 6 million QSOs in Gaia. But you can also extract a very pure sample of QSO by following the guidelines in the papers that I showed you. So here on this axis, I'm just showing an example of the spectra. So these are the BP and these are the ORP spectra of QSOs with different redshifts, okay? And you can see basically how the emission lines, okay, they will shift, okay, which is what it allows us to extract the redshifts. Okay, then there's the outlier analysis that I discussed earlier. So you'll find this information also in the Astrophysical Parameters table, because if a source has been marked as an outlier, well, then it'll be marked there with an information on what type of an outlier it is. But then there are dedicated tables, the AO neuron information and OA neuron XP spectra. And these are multidimensional tables. So for example, here, this is part of the OA neuron information table. And if you want to visualize these data, there is a tool that is available that is hosted at, I believe it's in Madrid, where they host the visualization tool to do this. So the outlier analysis is an unsupervised classification using self-organizing maps and it analyzes the 56 million poorest classification objects. So it takes the classification from the DSC that I showed earlier, and it finds those objects that really, maybe it's 0.5 of being a star, 0.5 of being a galaxy, so we really don't know what it is. So it takes these poorest classification and tries to organize them. And as you can see, when it organizes it, it groups the objects with similar spectra and similar information. And you will, in fact, not only find things that that outliers, but you will also find things that we know. For example, there are some carbon stars in here, or there are some QSOs, for example. Okay, but this allows us to do a more refined analysis of these things that we don't know very much what the objects are. So you'll find this 30 by 30 lattice of neurons, okay? And it'll also, and the spectra of each of these neurons is also available in this table. So now let's go to the interstellar extinction parameters. Okay, so there are 4 tables where you find this. Again, most of it's in astrophysical parameters. There's a few in astrophysical parameters sub. I'll explain briefly what the difference is here in this. But these are source-based. That means for one given source, object, star, whatever it is, we have a value for it. Then there are also these 2 maps, a total galactic extinction map and a total galactic extinction map optimal. And these are a heel-pix-based map, not source-based. Okay, so it provides you the extinction, the total galactic extinction, like in the line of sight. Okay, so the different dust and extinction parameters you will find, in particular for the source-based ones, are the extinction in the G band, the extinction in the BP band, extinction in the ORP band, and you'll also have this monochromatic extinction, which is defined at this wavelength called A0. So this is the value that's actually independent of what the emitting source looks like. Okay, so this is the fundamental value, and then depending on the temperature of your object, these values will be different. Okay. There's also the color excess, which is the equivalent to E B minus V that many of you will be familiar with. So this can also be calculated from these values here. So you can calculate any combination of these this reddening, this color excess from this extinction. And there's also the diffuse interstellar band that I mentioned earlier. So here's an example of this is when you look down on top of the galaxy, well, with the sun in the center. Okay, this is basically a map showing the equivalent width of the diffuse interstellar band measurement. This is as provided in Gaia DR3, with blue indicating very low values and red, orange, red indicating higher values. So you can see that as we move away from the sun, the DIB increases, which is what we would expect, because generally closer to us, there's less chance of having dust around us. But as we go further and further, of course, it's more a volume space, so you're going to have more chance of having dust. So this is the DIB. So you have individual measurements of this equivalent width as well. Now for the total galactic extinction map, I do not have a figure to show you here, unfortunately. So basically, it evaluates the total extinction in a line of sight. And what it does is it uses the GSP-FUD extinction. So GSP-FUD is one of the work packages that analyzes the stars. And it produces one map at a heel-pix level 6, 7, 8, and 9. And then there's a second map at a heel-pix level 9. And it's produced at the optimal heel-pix level. Okay, so if you're interested in extinction, these 2 maps would be of use to you. And in fact, we have also integrated the use of this map into this Python dust maps package to make it easier so that you can make a query directly on galactic latitude and longitude. Okay. Okay, so now I'm getting to the stellar parameters, which is what I'm going to talk about for the last 10 minutes or so. Okay, so this is, the most part of what we do in CU8, but not only. And these are in the astrophysical parameters and astrophysical parameters subtable. Okay, now the difference between these are basically that most modules will produce a result that goes here, but there are a few modules that produce supplementary results, so either based on a specific library or specific methods, and these go into this subtable. Okay, and this was done both for ease of use for the user, but also, in fact, for technical limitations, because this table was so big and there's a certain limitation that we can't have in a table in the archive. So the parameters that you're going to find are things like the following: effective temperature, surface gravity, global metallicity, iron abundance. Be careful, this is iron over metallicity, not iron over H, but you can easily calculate it. Iron over H. The alpha over iron and elemental abundances. So these are alpha Fe and X Fe. Of course, these things that I'm showing here are the actual names that you will find in the archive, so that would make sense. There's a spectral type. There are class probabilities of emission line stars, called class prob. There are evolutionary parameters, radius, absolute magnitude, luminosity, mass, and age. And there are a couple of more stellar parameters that I'm not going to describe in this slide. But if you look at these particular parameters, temperature, log G, metallicity, and radius, they are in fact produced. There are in fact multiple estimates of these. Okay, so let me briefly remind you that all of these look at stellar. GSP foot uses the BP and ORP spectra. GSP spec uses only the Rvs spectra. Okay, and then these modules are specific that look at maybe very cool stars or very hot stars. So, and this is the reason why you will sometimes find multiple versions. So if you look at the temperature, for example, you have one that's called TFF GSP foot, because this is derived from the BP-ORP spectra. You've got one from GSP spec, the Rvs, and then you've one from this ESPHS. So ESP is the special extended parameterizer focusing on hot stars, so OBA stars, and then the UCD are the ultra cool stars. So depending on what your use case, you probably might prefer to look at this ESP UCD if you're interested in the cooler part, because that will perform much better than, for example, this general parameterizer that just looks at everything in a global sense. Okay. And of course, for the very high resolution data, these results in principle are the same, right? But the spectra do not contain the same information. And so you may find differences between those parameters. Okay, and this is the same for the radius. So there's a radius that's derived from the flame module. Then there's a radius flame spec. Okay, so the radius from the flame uses the temperature from GSP foot. Radius flame spec uses the temperature from GSP spec. And there's also radius GSP foot. So there's a few of these parameters that have multiple values. And depending on what you want to do, you can choose which one you prefer. Okay. And we give guidance to which one you should use in the papers. Okay, so for the next 5-6 minutes, I'm going to go through just a few of the parameters individually so that you have a more global idea. So the first module looking at stars is GSP foot, okay? And basically it derives temperature, log G, metallicity, and extinction from the BP-ORP spectra. And you find results for 470 million stars. It's quite complete versus pure because we made a specific decision not to filter too much so that the user can do what they want. What we think might be junk is not junk to other people, right? Of course, there's not very much junk in there, right? It looks at temperatures between 2.5 to 55,000 Kelvin, but it uses one main method. And this is why I say if you want to look at very cool stars, you probably want to prefer to look at the specific module looking at ultra-cool dwarfs. Okay. Covers a range of extinctions, and it only analyzes to magnitude G of 19. Just a word of caution. So we have found that the metallicity less than -1 should be used with care. Okay. Now there has been a calibration tool that has been prepared and it will be available on DR3 so that you can calibrate this metallicity if it's important for you to go to lower metallicities. Okay. There are also 4 results in the supplementary table. So this supplementary table, these are based on results for the Marks, Phoenix, A, and the OB libraries, whereas the best one, the one that gets the best chi-square, will be in the main astrophysical parameter table. So here's just a comparison of the surface gravity with astroseismic surface gravities, which are very precise. So here are the dwarfs, and you can see that there's a very good agreement, so less than 0.1 dex in agreement. And then with the giants, there's a lot more dispersion, but this is normal. Even using classical spectroscopy, we have higher, less precision on these giants. And the biases are very, very, very low. Okay, so the GSP spec analyzes the Rvs spectra. So there will be results basically for G magnitude less than 13 or 14. And it uses two methods. Okay, so the main method will be in this astrophysical parameters table, and then there's a supplementary method in this subtable. So here's a comparison of the temperature, log G, and the metallicity with the literature. You can see that there's global agreement for these stellar parameters. They also do abundances, but there's not just the abundances. There's the upper lower confidence intervals, number of lines, and the line scatter. So there's all these parameters, and these are all of the abundances. So there's the alpha over Fe, which is an actual fitted parameter, not an abundance. And then there's all of these chemical abundances here available. Looking at the emission line star, so this ELS, so there are nearly 60,000 emission line stars, and you will find results for these in this class prob ESP ELS results, and these different results will tell you if it's a T Tauri, WC, WN, B star, Herbig, etc. Okay. Then there is also a class label that has been defined based on these class probabilities. But of course, you are free to choose your own class label based on what you consider as a limit for the probability. There's also spectral type from this module for 211 million stars. So they have basically all of the spectral types plus a carbon star spectral type. And then there's information in the flags about the quality. And then there's also the equivalent width of the H alpha line as measured in the BP and the ORP spectra. Now there's also information on hot stars. I know some of you are interested in hot stars here. So the hot stars module basically analyzes the BP, ORP, and the Rvs together if it's bright, or only BP, ORP on its own if it's too faint. And they do classical stellar parameters along with V sin I, and for about 3 million sources, okay, with magnitude up to 17.65. So in this figure, I'm showing effective temperature versus log G for sources for different clusters. So for example, NGC 2437, and you can see that the temperatures agree pretty well with the isochrones, and the same here, okay. And also, if you look at log G in temperature, so this Kiel diagram, you'll see this place here, and these are the horizontal branch stars. So we didn't aim to look for them, but we find these horizontal branch stars. Okay, I'm going to move I believe the slides, of course, will be available to you. So there's other spectroscopic parameters, but now I want to explain to you some evolutionary parameters. So these are found in the astrophysical parameters and the subtable. And so does not analyze the spectra directly, but we use results from GSP foot or GSP spec to produce a luminosity, a radius, a mass, age, and evolution stage. Okay, it uses the Basti stellar models. So you find 280 million sources in the astrophysical parameters table, and this will be based on the GSP foot temperatures. And then in the astrophysical parameters subtable, you'll find 5 million sources, which are based on the GSP spec temperatures for this temperature range. And here I show a comparison with the literature. So here I'm showing the radius from flame, in comparison to the radii from Pinsonneau et al. Using, I believe this is the Apocask radii. So these are pretty accurate. So you can see that there's very good agreement and scatter on the order of 0.05 to 0.1. And this is a comparison of the mass, so the relative mass compared to the mass from the literature. And this is a comparison with the Casagrande et al. 2011. And you can see that there is also a global good agreement with the masses. Okay, and just one final slide. There's another module here, MSC, and what it does, it analyzes all of the sources, but it treats the BP and the ORP spectra as one unresolved binary. So it's assuming it's an unresolved binary. And there's results for 330 million sources. So it produces a distance, extinction, and metallicity. So for one unique. And then it fits the temperature and log G for 2 individual sources. And here there's a comparison of the temperatures from those of Traven et al. And El Badri, which are binary catalogs. And you can see that there's a global agreement with the temperatures. Okay, so I'm almost finished just summarizing. So just to remind you, in the astrophysical parameters in Gaia DR3 is only one component of Gaia DR3. But within this, there are many different categories: the extinction, classification, outliers, redshifts, and then all the stellar parameters, the spectroscopic and evolutionary ones. Okay, so in summary, we have 1.6 billion classification probabilities, nearly 500 million spectra, stellar parameters. Then there's chemistry from the spectra, there's redshifts. And the other products I didn't talk about in a lot of detail are like things like activity index, the H-alpha emission equivalent widths. There's some hot star classes of stars. And there is also the 2D map of total galactic extinction and the outlier analysis. So compared to Gaia DR, so this is DR3 in 2 weeks from now. But to remind you, Gaia DR4 will be based on 66 months of data, so 5.5 years of data, which means higher precision, better calibration of the spectra, and a better handle of the systematics and uncertainties. And this means we get much better stellar parameters down to a magnitude of 21. And yeah, just to remind you what's in Gaia Data Release 3, a brief reminder of all of these things. And muchas gracias. Que disfruten la Gaia DR3. Thank you.
Thank you. Thanks a lot, Orlagh, for this very complete description of what we really get. Okay, so let's go to the questions. I see Carmen has questions, so go ahead.
Thank you, Orlagh. This is very exciting. One technical question. I am, something that I need desperately are extinction values for individual stars. So this AP, so to just the redden, individual stars. So this AP, AG, ABP, could this be used to do this work directly?
Exactly. So, so the extinction is derived from the BP and the ORP spectra, along with the temperatures and the log G and the metallicities. Okay, so there will be certain regions that it's a little bit that maybe if there's too much extinction, there may be problems with the temperature extinction correlation. But in general, these can be used on an individual basis.
Mm-hmm. And is there any so to what color range and absolute magnitude range they will be? So it will be basically for the whole CMD, or there are limitations in terms of a spectral type, for example?
So it's based on the model libraries of the Marks, which is roughly 2,500 to 8,000 Kelvin. The Phoenix, which is I think 2,500 or 4,000, I can't remember, to 10,000. Then there's the A star libraries, which is 8 to 20,000, and the OB libraries, so up to 50,000. Okay, so you can go into the supplementary table and choose the extinctions from the stars that you think is the best for those, and you can use them. Okay. So it's basically anything from 2.5 to 50,000. But there are also, so I mentioned that there's another module that looks at hot stars, for example. They also produce an extinction, okay? And there's, depending on the magnitude, sometimes they analyze it with the Rvs. So you might get a little bit higher precision on the extinction because we can use the Rvs and the BPRP to decouple the temperature extinction degeneracy. Okay.
Okay.
But
And in
yes,
terms
you
of
could use them.
and in terms of ages, I guess this will be isochrone fitting kind of thing,
Exactly.
or
Yeah.
And then so is there a limitation for the kinds of stars that you are doing this for, and how many millions they will be?
Yeah. So for the ages, yeah, exactly. In fact, a solar metallicity was actually applied. A solar metallicity prior was applied because of this, what I mentioned earlier, this metallicity issue that we found with GSP foot. So it was safer to apply a solar metallicity prior to get accurate results for any stars than to get inaccurate results for more stars. But the approach is classical. We use luminosity, temperature, metallicity. Okay, so there are limitations. I mean, if you use astroseismology, you will get much higher precision. Okay, but there are ages for 120 million stars.
Okay.
But
Okay,
it's an
thank you.
isochrone fitting method, right?
Okay, thank you.
Thanks. Okay, so I see Diego has a question.
Yeah, so thank you for the very interesting talk. And I think my question kind of follows what you were just talking about. So you said that I think temperature, log G metallicities will be derived, at least for the cooler stars, from the Marks and Phoenix models, right? But then when you talked about ages and luminosities, you talked about the Basti model. So I guess my question is, how self-consistent are these set of parameters for a given star?
Yeah. So okay. So the spectroscopic parameters are derived from models of stellar atmospheres. Okay. So temperatures, log G's, metallicity, and extinction. Then using just Gaia data itself, you can derive the luminosity with using a bolometric correction. Okay, the bolometric correction has model dependency. It's Marks and A libraries. Most of the stars actually end up their best temperatures from Marks, right, in general. So the luminosity is kind of independent of this. Then you've got a radius, but it's derived from the temperature and the luminosity, okay? And then that's used to infer, the luminosity and temperature is used to infer the masses and ages. Okay, so one is atmosphere models and the other is evolution models, okay? But of course, like they're already transferred from observable to fundamental parameters, right? Luminosity and temperature before comparing with the evolution models.
Okay, so then we have Attila.
Yeah, thanks for a great talk. Can you hear me?
Yes.
Yes, okay. Yeah, so I had a question actually. I wanted to know what is the area of overlap between TESS and Gaia?
Complete. So yeah, no, in fact, my PhD student is working precisely on that, TESS and Gaia, because Gaia observes everything in the sky, and TESS is almost a full sky coverage. Okay, it avoids the ecliptic plane, I think it is. Yeah, so there's almost a full coverage. The difference, of course, is yeah, TESS has very large pixels. But you can use the Gaia data to help you decide if the nearby stars are going to contaminate your TESS data, actually. So there's a complete coverage overlap. Yeah.
Okay, great.
I think it's a very, very nice combination of missions, personally. Right. Yeah.
Perfect, thank you.
So then I see Paul.
Hi, Orlagh. Thank you for a very nice talk, very comprehensive summary. And I have a question. It might be a little bit off your work package, but on the binaries, there has been a bit of confusion in the community. What are the Gaia products in DR3 for binaries? And the second question is, how independent are the astrophysical properties for a confirmed binary? So how much can we rely on it?
Yeah. Okay. So In Gaia DR3, there will be, let's say, astrometric solutions and radial velocity solutions, and transit, solutions for binaries. Okay, so these will appear in specific tables in DR3. Okay. Now, concerning the astrophysical parameters that we produce, okay, so we produce them assuming it's, we use a mean spectrum. So depending on what the luminosity ratio is of your binary, so what's going to dominate the spectrum, the results can, you can use our results if the luminosity ratio is quite high. But if you've got two equal mass luminosity, or equal mass stars in a binary, and it's a binary solution, well, then our astrophysical parameter is probably not going to be quite right. Okay, so you will need to look at the luminosity ratio, but that information you will get in the specific tables in the archive. But also there is, so along with the archive and all of the papers describing the data, there are a few papers that are called performance verification papers. And this is where we give actual scientific examples of how to exploit the data. And there's a specific science performance verification paper that is dedicated to binaries. So that will be, I guess, probably the first place where people will look to see how they should exploit those products.
Okay, thank you. So you said solutions. Are there also time series or only complete solutions available for radial velocities, for example?
Okay, so for radial velocities, no, it's just the solutions,
Okay.
right? The only time series you will get is whatever is classified in the variable, the variable group, and some variables could be binaries, right? But you have to look into the variability tables. They provide the time series of the photometry.
Okay, thank you.
Okay, so maybe let me jump on this because I'm interested in variable magnetic stars. So first of all, so you're saying that we can get time series of like asymmetry or something like this. Okay.
So yeah, so some of the variables, yeah, you can get time series. But let me see if I can maybe show you. If you want to access the time series, so these are what's called data link products. So if you do a query, here, let me bring up, let me see if I can bring up an example here online. Okay. I need to sign in because I know if I try to do a query, I am not going to be, I'm going to get the query wrong. So let me show this here. Share screen. Should work. Okay, so here, let me just do this. This query here. Okay, so here I've done. Let me see. I'm trying to get one that makes sense. Of course, because I'm using Zoom, things are taking. Let me see. Okay, so here's one. Oh, sorry, this is in the way. So if I run this query, okay, I get some result here. And then I can look at this query. So if you want to keep all your queries, you need to sign in. You can create an account, right? And this will give you the information about the query, the job. And then you can upload, create a user table. You can download the results. You can share the results. But if you click here, you will see information about all of the other types of data that are available, right? So if there's so if there's photometry available, for example, okay? So you can click on this link here. This is one way of accessing the time series. There is also lots of information on accessing these data link products using Python. So there's Python scripts available to help people do that automatically, because if you do it directly on the website, you're limited to the amount of data. But if you do it through Python, you can, I think there's unlimited amount of data, and you can just run your queries, you know, let it run. So, but that information will be available to show people how to do that.
Okay, great. Any other questions? Paul.
Yeah, okay. Just a question into the future. What will Gaia DR4 and DR5 give us then? If this is all results, I think.
Yeah, so Gaia DR4 already, what you have in DR3 will be improved because we have twice the amount of data, higher signal to noise ratio, more precision, a better understanding of systematics, etc., etc. But also there will be the epoch data. So there will be the individual radial velocities, the individual spectra, the individual. So what the spectra that are released are the mean spectra, right? But you will get the individual ones in DR4 as well. And then DR5 will be based on basically twice the amount of data. So it'll just go much higher precision in photometry and astrometry, and then everything that comes after that. Okay. So yeah.
Still have some time to wait, I guess, for this. So yeah.
Enjoy DR3 first.
Yes.
And then give us feedback so that we can make our products better. I mean, you know, we produce on millions of sources and we cannot look at everything. We look at specific sources or in certain parts, and we will get things wrong, right? But if there's some systematic things wrong that we haven't noticed yet, do email us and tell us so that we can fix that the next release. Okay, so we require feedback from the community to get better products. Okay, so don't hesitate to give me an email.
Okay, great. Okay, well, I guess thanks again for your talk.
Thank you. Thank you very much for listening.
In a bit less than 2 weeks then.
Yeah, enjoy DR3. Yes. Thank you.
Thanks everyone for joining. Hopefully next time, Orlagh, you can come and visit us at the AC.
I would love to do that. Yeah, definitely.
Okay,
Thank
well,
you.
thank you.
Bye.
Bye.